Hi everyone, and welcome to Eric's Electronics Workbench. So on the bench today, I have a pair of Kenwood KM-208 audio power amplifiers. Now these amplifiers were manufactured around 1989 to 1990. So as I'm making this video in 2025, they're about 35 or 36 years old. Now, these amplifiers tend to be a little bit overlooked nowadays, but they're a very capable audio amplifier and they have very good specifications. So they're rated 150 watts per channel into 8 ohms. They have a very good signal-to-noise ratio and very low total harmonic distortion. And they use all discrete components in the audio signal path, so they don't use an integrated circuit type output stage. Again, all discrete components. They have a massive transformer. They're actually quite heavy. And they have very large filter capacitors on the power supply rails. So again, just a very nicely made consumer-grade type audio amplifier. So I definitely think it would be worth the time and effort to make one of these amplifiers work again. I think it'd be a nice addition to have my collection of audio amplifiers and to be able to enjoy the amplifier. I'm sure it sounds very nice. So you see two amplifiers sitting here, and you might be thinking, well, why not fix both of them? What's going on? So I'll explain. This amplifier I picked up several years ago, and it was sold as is, untested, unknown condition. And maybe the seller knew a little bit more about it, but nonetheless, that's how it was listed. And it was sold very, very inexpensive. So I took a chance on it and thought, if I can make it work, great, I might have a nice amplifier. So when I received it, I was very happy with the cosmetic condition. There are no scratches on the top cover, no dents. The front panel is extremely clean. There's no scratches whatsoever. The display window right here, it's plastic. It's prone to getting scratched or damaged. It looks like factory new. It looks like the day it was made. So, again, cosmetically, this amplifier is in fantastic condition. So when I receive something like this, the first thing I do is take the top cover off and take a look around inside. It was pretty dusty, cleared the dust away, and very glad that I didn't power it up, because this amplifier is a complete disaster on the main circuit board. So there's two heat sinks, one over here and one here. So this is one channel, this is the other channel. And on this channel, almost every transistor is completely destroyed, shorted out. One of the transistors is completely blown off the circuit board. A number of resistors are burned open. It's really one of those cases, the more you look, the more damaged components that you find. So there's even some traces on the bottom side of the circuit board that are damaged because some of the components got so hot. So when I saw that condition, I thought, well, maybe I can start replacing components and fix it back up again. So I started kind of pricing the components and quickly found that many of the transistors are obsolete. They're very hard to come by, particularly the output stage transistors. A lot of the transistors that I was coming across, I didn't even think that they would be genuine originals. They were probably fake type components anyways, so I wasn't really happy about that. I kind of set the amplifier aside. I thought, I'll have to think about this and what I want to do. And in part, when I was totaling up the cost of the components, it was really looking like it was just not economically feasible to rebuild, basically the one channel. And I don't even know on the other channel if it works or not. I've never powered up this amplifier, but I didn't like the approach of trying to repair that one channel, just again, given the issues of the obsolete transistors and just the cost of all the components. So I set the amplifier aside and I thought maybe someday I'll either be able to get the parts over time and build it up that way. You come across the transistor here and there kind of a thing, or maybe I'll come across a whole nother amplifier that I can salvage for parts. That actually seemed like probably the more realistic way to do it. Well, now we have this amplifier sitting over here, which I picked up a little bit more recently. So that amplifier was sold as is, not tested, but that it's supposed to power up. So, that's a start, but that leaves a lot of unknowns as well. And it was sold also very inexpensive. Now, I knew when I purchased it that the cosmetic condition of this amplifier is in very poor condition. So there's a big dent right here in the top cover. Some really bad scratches on the front. There's a kind of a gouge right here in the metal. Another scratch right here. There's a scratch right in the top. I don't know if all of that is really visible on the camera, but just cosmetically, this amplifier is in very poor condition. There's some dents on the back panel, almost a little bit of like a rust or something on the back panel as well. And two of the feet are missing on this amplifier, which is why it's sitting at kind of this angle right now. My thought is that if this amplifier works, we could take the the circuit board that's in here and move it over to this amplifier. I don't know about moving individual components over. I think it would be better to move the entire circuit board over. And you might be thinking, well, wait a minute, why not just take this cover and put it over here, move this front panel, move it over here? Well, the problem is that the back panels on these amplifiers are not the same, even though the models of the amplifiers are identical. And I'll show you the back panel and what's going on. But I don't quite like the back panel on this amplifier. And this amplifier, it looks like factory new, but there's no way to use this panel on this amplifier because of the differences. So I think building up this amplifier is the better choice, removing this circuit board and then again moving this board over here. Assuming, again, that this amplifier actually works, and that's yet to be known. Also, what I don't know is, does this transformer work? I have no idea. This needs to be tested. With the damage that this has, could that have damaged this transformer? Possibly, I don't really know. If it did damage this transformer, there's this transformer. Hopefully that would work okay. But again, it's going to just be some switching around of parts and pieces and testing to see what actually works. Now, don't think this entire video is just going to be about swapping around parts and pieces. There's definitely going to be troubleshooting. I'll show you some of my techniques that I use when I'm testing components, taking measurements. Obviously, the amplifiers need to be tested. When this one is completely done, it needs to be tested, but this one needs to be tested as well to see if we're taking good components and moving them over. So all of that testing I'll share with you as well. So if you're new to electronics and like to learn a few things about testing, definitely stick around. If you're interested in audio amplifiers and how to test them, of course, we're going to have to set the bias and check that. All of those types of tests I'll show you. So stick around. There's a lot to cover here. So I'll reposition things and let's take a look at the back panel and I'll show you the difference that's going on there. All right, here's a look at the back panel on each amplifier. So this top unit is the one that is in nice cosmetic condition but has the damaged circuit board, and the bottom unit is the one that's in poor cosmetic condition. So starting over here, these two RCA connectors are actually bent that direction. So there's a bend in the metal right here. I don't know if there's any damage internally, but that would certainly need to be looked at if this panel were to be used, because again, the metal is actually bent. Now, what I don't like about this panel is that along this bottom edge right here, there's some kind of a rust or corrosion that's setting in. It may not be real obvious on the camera. You almost have to turn the amplifier upside down to really see it. But perhaps this, was kind of damp or wet at some point under here. And again, this corrosion that's sort of setting in on here, there's really no way that you're going to reverse that or even clean that off. It's not just a dirt or something that's on the surface. It's actually something that's affecting the metal. So I wouldn't want to go through all the trouble of repairing and servicing the amplifier just to have this panel on here with this sort of corrosion that's on there. Now, the difference on the panels, you can see over here, there's a switch right here and a switch here that are not present on this other unit. So I believe that this is an international version of the amplifier, where this amplifier was intended for sale probably just in the USA or perhaps North America, because this is only for 120 volts, where this one has a line voltage selector switch for 110, 120 volt or 220 to 240 volt. So that switch is just changing the primary taps on the power transformer. Now, this other switch is kind of interesting because it's a speaker impedance selector switch, which again is not present up here. And I don't really know what it was about the design of this amplifier that they felt that it needed to have that switch where this one doesn't have it. But right here it says less than 8 ohms, and this is 8 ohms or more. But actually all it's doing is changing the secondary taps that are used on the power transformer. So in the higher position where it's 8 ohms or more, it's selecting the higher voltage taps. And then on the lower impedance, it's just the lower voltage. Where on this amplifier, it's always using that higher voltage tap. So this actually has two different power transformer in each of these amplifiers. But given what I know about this switch and what these are doing on here, the transformer that's in this unit could be moved over to this amplifier, but the taps that are being selected by these switches could actually just be hardwired, and so you're not changing them. So if the transformer in this unit with all the damage on the circuit board, if the transformer has actually been damaged, then this transformer could be used, and although it's slightly different, I think it could be made to work. So we'll have to check that out when we get into the units and do some tests and measurements. All All right, so let's take a look at the damaged components in the amplifier that's otherwise in nice cosmetic condition. Actually, before we do that, let me just grab the top cover real quick here, and you can see this area right here. So this area inside the top cover, you can see the sooty, discolored mark right there. So when those components let out the smoke, it definitely left a discoloration inside the top cover vent. So I'll set that aside. Let's get back down on the circuit board here. So taking a look at the components on the board, you can see this resistor right here has been overheated. This resistor is overheated, discolored. This resistor is discolored. Right here on the board there should be a transistor, but all that's left are the three legs or the three leads of that transistor. So the body of the transistor is completely gone. So there's a pretty drastic failure right there. You can see the board is discolored. It looks like right in this area here there's another 1/8 watt resistor that's discolored and overheated. In this row of resistors right here, so some more 1/8 watt resistors. Just point from the other side right here, but you can see this resistor right here has been overheated. This possibly was a diode, I'm not really sure. Whatever component it is, only half of it's there. So a pretty drastic failure again, and the board is discolored. And actually it's kind of loose, so the trace on the other side of the board is damaged on this component right here. And then here's another resistor right there that's defective or very overheated. And it's blocked from the camera view with this metal bracket right here. But in this row going back this way right here, there's another resistor that's overheated. So quite a few components in this area, all the resistors that have seen better days. Now, I don't know about the capacitors. I wouldn't trust them. They would need to be changed. In fact, in the circuit board on the other amplifier, if that board works out and is in functioning condition, and we're able to use it, I'm going to change the capacitors anyways, because the age of the amplifiers, it'd be a good idea to freshen up the capacitors. So I wouldn't probably need to change these large filter capacitors. Oftentimes those last a very, very long time, but all of these small electrolytic capacitors that you see down here on the board, those should be changed out. And that's a minor thing to do, so I'm not too worried about that. And in repairing this circuit board, all of these resistors that are defective, and even the defective traces or the damaged traces on the board, that could be fixed. It's a little bit time consuming to repair those traces, but again, it is possible to do. The resistors are certainly available. The capacitors, not a problem to get those. The real issue is the active components, or all of the transistors. So I'll show you some of them that are easily measured, and you can see how they're defective. So I've already gone through and checked all the transistors on this channel, and basically all of them are defective. Either they're shorted or they're open, kind of one way of failure or the other. I think there's one or two transistors that actually survived, but by and large the majority of them are defective. And the ones that actually did test good, I wouldn't trust them to keep them in the circuit at this point. So let me reach over here. I'm going to turn on my multimeter. So, and the test probes right here, if I take these and just touch these together, you can hear the beep. So that's just the continuity mode. So if I reach down here, so this is one of the output transistors right there. If I touch across the leads of the transistor, so dead short right there. And if I go to the other output transistor, which is over here on the heatsink, there, so dead short. So this transistor right here is easy to reach. It stands up off the board. So if I touch across here, it's right there. So that transistor, another dead short, just 4 ohms across it. This transistor here stands up easy to reach here. Let's see if I go right there, another short on that transistor. So again, the list just goes on. There's many transistors that have failed in this channel. So basically a cascade type failure. So it's hard to say where the original failure point was. It may have been the output devices that failed first, or maybe it was on an input stage. It's anybody's guess at this point, and even why it would have failed. Was it a power surge? Did the line voltage rise up too high? Was there some kind of a short circuit on the output to the speakers? There should be protection circuits in here that would protect against that. Did something severely overheat? Was the bias set wrong? There's any number of things that really could lead to such a kind of a failure like this. But the stages in the amplifier are all direct coupled. So when one stage fails, it can take out the next stage. And it's something to remember if you're troubleshooting an amplifier, because you can have this cascade failure and you don't want to overlook a preceding stage or a following stage that could be faulty. Let's say you replace these output transistors and didn't test anything else. You'd be in for a nasty surprise when you turn on the amplifier. If you had other transistors that were all defective, it would probably just take out the transistors that you just replaced. So just, keep that in mind if you're troubleshooting an amplifier, particularly when they're direct coupled between the stages. All right, so the next thing I need to do is to test the transformer in this amplifier, because I've never checked the transformer. I've never powered up this amplifier. And I'd like to know if the transformer is functioning correctly and has the right voltages on the secondary side. So I'll disconnect the wires that are on the secondary side. Let's take some readings. We'll take a look at the schematic and see which wires, they're color-coded, and I think they have some numbers as well on the circuit board. So we'll match that up to the schematic and see what should we expect and then what do we actually measure. All right, so we'll do that next. All right, so here's the schematic showing the power transformer in the audio amplifier. So let's see what voltages we should expect to see if the transformer is working correctly. So this is the transformer on the schematic, and this is the primary side, and this is the secondary side. So on the secondary side, you can see that there's a winding right here, and then another winding that's center tapped. And on this winding, it says 0 volt and then 25 volts. So when you see 0 volts, it means that this 25 volt is just referenced to that point. So we should see a voltage on this winding that's very close to that 25 volts, possibly a little bit higher because it would be unloaded. And then this is a center tapped winding, so it's 0 volts on that center tap. And then it says 48 volts, and then in parentheses 58 volts, and then the same thing on the other side. I think we'll be measuring something close to the 58 volts, if I'm understanding correctly in the amplifier. I believe it should be pretty close to that 58 volt value. Now you can see I changed the color coding that's mentioned right here. So this is red and this is black. So the center tap is black, but one side of the transformer is red. The other side right here, it was marked as orange, but I actually changed it to blue because in this amplifier, when I remove the wires off the circuit board, it is actually the blue wire. It was not orange. And then on this other secondary winding right here, they had both wires marked as blue, and they are not. They're both orange. So I just made that change because I'll need to follow that color coding, when I reassemble with the other circuit board, assuming that the other board works out okay. Now, over on the other side right here, this is just the primary side. Nothing too exciting going on there, anything unusual. It's just the AC line coming in, the main power switch, auxiliary outlets. So nothing to really worry about or measure on that side. So we'll just be concerned with the secondary side over here. And on that secondary side, right here, this is the center tap goes over here to the circuit common. And you can see this bridge rectifier. So you have one side of this center tapped winding coming over here to the bridge rectifier's AC input, the other side right here coming over to the AC input. And then the output of this bridge rectifier is the main DC rails for the power amplifier. And this is an auxiliary winding. It comes down here to this other bridge rectifier. So it's just, powering some auxiliary circuits. Now, if we take a look on this other part of the schematic over here, this is for that international version, which is that other amplifier with the switches on the back panel. And you can see right here on the primary side, it's a different transformer because the primary side has a split primary. So this is the switch right here that selects the 120 volt or the 240 volt operation, and it just either connects these in series or parallel. So very traditional way to get, the dual voltage type input. But the secondary side over here is also a little bit different. You can see some added complexity. This switch right here is that impedance selector switch. And essentially what it's doing, we have that 0 volt center tap right here on the winding, but we have some extra voltage taps on the winding. And you can see there's a 58 volt tap, and then there's also the 48 volt tap. And this switch is just selecting which of those taps are used. So the main DC rails in the power amplifier would be changing depending on the setting of that switch. But again, that's not used in this setup over here. And I believe the power amplifier boards are otherwise identical, so I'm not sure why they chose to use this setup and this switch on the international version, but not on this other version. So anyway, just a slight difference there. And to do the test, I'm going to plug in the amplifier, into my current limited isolation transformer and variac, and I have the transformer secondary disconnected now, so the leads are just floating, and I'll move the camera over to that in just a moment. You'll see that. So it's connected to my variac. I'll bring up the voltage slowly, but it's current limited through an incandescent lamp. So if something is drastically wrong with this transformer, it'll just make that lamp glow very brightly. So it's a 150 watt incandescent bulb, so we don't want to see it glow at all because there is no load on this transformer. Now, if you are following along, you're absolutely doing so at your own risk. There's obviously exposed AC line all over the place in these power amplifiers. I don't think there's any heat shrink whatsoever inside the amplifiers. There's really no protection, so a lot of exposed AC line. Definitely don't want to come in contact with any of that. So you do need to use an isolation transformer when you're working on these, but an isolation transformer doesn't protect against all shock hazards because there's still elevated voltages on the secondary side of the transformer. And if you come across both AC lines off of the isolation transformer, there's still a shock hazard. So definitely take care and be safe if you're working on one of these amplifiers and following along. You're absolutely doing so at your own risk. All right, let's take a look at the transformer and take some voltage measurements and see if it's actually working. All right, so I have the transformer secondary wires disconnected from the circuit board. So you can see the wires just kind of floating around over here. So we'll take some measurements in just a moment. Now I noticed there's a fuse on this circuit board right here. I've never tested that fuse, so if that fuse is blown, obviously nothing's going to happen. So let's check that first before we do anything else. Get that turned on. So it's in the continuity mode. So if I touch this together, it just beeps. So of course, the amplifier is not powered up right now. So yes, no problems there. That has good continuity through the fuse. So what we're going to do is put these test clips on right here, these alligator clips that go on the end, so I can clip the meter right onto those secondary wires. So let's go over here, go measure, and we want to go to AC volts. So we'll just start with this auxiliary winding, which were the two orange wires. So I don't want anything to short out or touch together right there, so that should be fine. All right, so take the amplifier, and this is going to plug into the, again, the current limited isolation transformer and variac. Right there. All right, the incandescent lamp is switched into the circuit. Turn the variac on. All right, so I'm going to start to increase the voltage. And yes, we do see voltage, so that's very good. And the incandescent lamp, it's not glowing at all, so that's a very good sign. So that's 60 volts on the AC line. There's 90 volts. And there's 120. So that looks perfect. So 27 volts on that secondary winding. So that's very close to the value that's on the schematic, and the incandescent lamp is not glowing at all. And the watt meter on the variac is just indicating a few watts, so no problems. It looks perfectly fine. All right, so I'm going to go ahead and turn the variac down to 0 again, turn it off, and I'm going to reach over here and let's go over to... So the black wire is the center common. We'll just put it one side right here. Okay. Same thing, turn this back on. Turn this up a little bit quicker this time because we know it does not have any short circuits. So there's 120 volts on the AC line and perfect, 53.8. So again, I'm looking at the schematic over here, and the value was 58 volts. So very close to the specified value. Looks like the line voltage, yeah, right at 120, so 53, 54 volts. So no worries, that's perfectly fine. That's very, very close. So turn that back down, turn that off again, and just go over to the other wire right there. Okay, variac. Turn back on, go back up to 120 volt line. It's right there, 120 volts. And look at that, perfect, 54 volts. So it's very important that those be balanced on each of the sides around that center tap. You'd want to see an equal voltage. So both sides are looking right about 54 volts. So perfect. I would say this transformer is functioning correctly. So that's very good news. It didn't take out that transformer with whatever was going on the circuit board and all those other damaged components. So now the next thing we need to do is to take a look at the other amplifier and see if it's actually functioning, because again, it was supposed to power up, but I don't know anything beyond that. So we actually need to put an audio signal into it if it does in fact turn on, and if put an audio signal in, check both channels, see if it actually can meet the rated output power. So connect a dummy load, connect it to an oscilloscope, see that it doesn't have any severe distortion or other issues going on. So I'll do that test setup next and kind of take you through that setup, and we'll see if that other amplifier is working the way that it's supposed to. Also, let me just point out one thing again about the kind of the shock hazard that you can come across in these amplifiers, particularly more higher powered type amplifiers like this. You can see that voltage, 54 volts, and you wouldn't want to come in contact with 54 volts. But turn this back down again. If I go, instead of this, go over to this right here. So now we're going across the secondary side. Instead of just from the center tap, we're going across the full secondary side. So turn the variac back on again here and turn this back up. So now we're going up to the 120 volt line again. And you can see, look at that voltage, 108 volts. So 108 volts, I mean, that's a lethal shock hazard. You would not want to come in contact with that. So you have to remember that when you're working in an amplifier like this, there is a very dangerous voltage on the circuit board, the DC rails in the amplifier, and you have to be very, very careful, that you don't come in contact with those DC rail voltages or across the secondary of that transformer. Don't think that the transformer is isolated and that it's perfectly safe and that there are no shock hazards, because there are definitely elevated voltages in the amplifier. So just keep that in mind. All right, now what I need to do is test the amplifier that's in poor cosmetic condition. So to initially power up the amplifier, I'm going to use my isolation transformer and variac, and I'm going to current limit through a 150 watt incandescent lamp. Now, I'm not going to bring up the line voltage slowly, so I'll just preset the variac at 120 volts. We'll hit the power button, we'll see what happens. But if there's something seriously wrong in the amplifier and it draws excessive current, or at least tries to, then the incandescent lamp will just glow very brightly. We can shut things down at that point. But if it's working correctly, that incandescent lamp will just have an initial bright, kind of a glow when everything turns on, that initial surge current, and then it should just drop down and just have a very dim glow to it. And then if that works that way, and it seems like the amplifier power is up okay, then I'll switch the incandescent lamp out of the circuit. I'll make the connections to the dummy loads, the signal generator, the oscilloscope, and then we'll do a power test on the amplifier. We'll look at the output waveform and go from there. All right, so first thing, let me just get this cord right here and get this plugged in. So go over here. All right, so that's plugged into the isolation transformer and the variac. Power switch is off. So get the variac is set all the way up here. So the mark, it's right on 120 volt mark on the dial, so that's good. Let's go ahead and switch on the variac. Okay, so the incandescent lamp is in the circuit right now, so it's in series with the AC line. Let's see what happens. All right, so it appears like it turned on okay. It looks like that lamp did have an initial surge when it turned on, and it's basically gone down. I can't even see it glowing at this point. So it's drawing, very little current. The watt meter, let me go over here and see. Yeah, the watt meter is extremely low. Switch that over to the lower range, and it looks like it's drawing about 15 watts right now. So that seems very reasonable. There's, of course, the idle current. There's going to be some power dissipation in the amplifier, so 15 watts doesn't seem like a problem at all. So I'm going to reach over here and switch this out of the circuit. So now it's on just the normal line voltage with the incandescent lamp is not in series anymore. And yeah, the power is still right around 15 watts. Maybe just went up just a little bit higher. When you have an incandescent lamp like that in series, there's always a little bit of a drop in voltage across the lamp. Even if it isn't glowing, you'll lose just a little bit across that lamp. So, looks good so far. Let me make some connections with the signal generator, get the oscilloscope, the dummy load resistors connected, and we'll try a full power output test. Also, when you test an amplifier like this, you don't want to have that incandescent lamp in series when you're actually doing the power test, because it would be trying to draw possibly many hundreds of watts of power, and you don't want to run that through the incandescent lamp. So if you are using a dim bulb type test setup, you're really only doing that for that initial turn on and the initial testing, just to be cautious and that you're not drawing excessive current. But when you actually do power test or something on the amplifier, you definitely need to have the bulb switched out of the circuit. So let's take a look at the signal source used to test the amplifier. So I'm going to use the BK Precision 4062B, which is a dual channel function and arbitrary waveform generator. Now, of course, I'm not using the arbitrary waveform generator portion of the instrument for this test. You can see the output frequency is at a fixed frequency of 1 kilohertz with a sine wave type output. Now, the frequency can be varied anything from, say, 20 hertz to 20 kilohertz, would be the typical audio spectrum that you would use when testing audio equipment. Now, you might also consider using a dedicated audio signal generator, and that can have advantages. Oftentimes, audio signal generators have a very pure type output signal, so very low total harmonic distortion, and other features that can be handy when you're testing audio equipment. But it is very common to use a function generator, so I'll just go over a few pointers to keep in mind if you are using a function generator. Now you can see this does have 2 outputs, but I'm only using this one output. It goes into this Y adapter and it just divides off to these 2 coax cables. And I want the same input on the left and right channels of the amplifier when I'm testing it. So this is the easiest way to do that. If I wanted different, for example, amplitudes on the left and right channel, then of course you could drive one channel from this output, the other channel over here. That would give separate control. Now, something that I'm often asked is, can you use 50 ohm coax cable like this when you're testing audio equipment? And the answer is absolutely, it's not a problem whatsoever. So these have B and C connectors on one end right here, and then the other end of these coax cables have an RCA connector, so it plugs right into the back of the amplifier. But the 50 ohm impedance of this coax is not a problem when you're testing audio equipment. These are shielded cables, which of course is important, but any audio cable that, for example, an RCA patch cable would have shielding on it. So you want the shielding, but the idea that these are 50 ohm coax cables is not a problem. Now, the input impedance on the amplifier is very high, and again, not an issue. The output on the signal generator is a 50 ohm internal impedance of this function generator, but it's not an issue. And you can see right here, it says high Z, which means high impedance. And the reason that this is marked here as the high impedance output is because that affects the voltage on the output. So that is very important to keep in mind. So right now you can see this is set to 10 millivolts RMS, but this is with the high impedance mode that's selected right here. If I hold this button down, see what happens? It goes to the 50 ohms. Now, it didn't change anything inside this function generator. Okay, this still has a 50 ohm internal impedance. But you can see that the voltage dropped in half. So instead of 10 millivolts RMS, it's now 5 millivolts. Well, that's assuming that this is now loaded with a 50 ohm output impedance. So this would be loaded down. And if you're doing RF work where there's a 50 ohm impedance on here, then you would of course want this 50 ohm so that the voltage reading up here is correct. But again, we are driving into a very high input impedance. So on any signal generator or function generator, when it's unloaded, the voltage typically doubles. And when it's loaded down to that 50 ohm output impedance or output load, and the voltage will typically drop about half. So it's important to keep that in mind if you have a voltage that you're expecting to come out of your signal generator. If it doesn't have this ability to change the voltage with the impedance setting like I was just showing, then keep in mind that it's basically going to either double or half depending on which way you're looking at it. But something, if that's causing some confusion or some troubles, you could use an adapter like this. So this is a feed-through type termination. So this has a 50 ohm internal termination inside, but it just passes through. So you can see the other side right here gives you that B and C connector output. So if you were to use this and set this to 50 ohms, the output of this adapter would then be half the voltage, or it would be down to the that 5 millivolts RMS. So it would basically keep the voltage in line. So for example, I'll go like this. If this is set to the 50 ohm output, and then I connect this on here, now the output on this is going to match this voltage, because this is now loading this with the 50 ohm output. So keep in mind, if this is set to 50 ohms, this is only correct on this output voltage when this is actually loaded down. And the amplifier is not loading it. The amplifier has a very high input impedance. It's not offering that load. So the only way to make this output match on the 50 ohm output is to actually load it with an adapter like this, if necessary, or go like this, go back to the high impedance, and now when this is unloaded, it will match that voltage. So that's often an area of confusion as to what voltage are you actually getting out of the instrument. So hopefully that clarifies that and helps you out if you do need to have a certain specific output voltage. And oftentimes in testing, you'll have a service manual, it'll say, set the output voltage to say 100 millivolts RMS, something like that. And it's very important to have the correct level. And on the topic of 50 ohm source and 50 ohm load impedances and 50 ohm coax cables, the general rule of thumb is that if you're working with frequencies above 1 megahertz, then you do need to start watching the source impedance and the termination impedance, or the load impedance, and also the coax impedance. All of that comes into play, because if it's not properly matched, then you can start to get standing waves and other undesirable effects. But in the frequencies that we're using with the audio, 20 hertz to 20 kilohertz, you're just simply not going to have those types of effects on a coax cable. So the idea of a 50 ohm coax cable with a very high termination impedance, in this case the amplifier, is not a concern whatsoever. Now, something else to keep in mind is that on the function generator, or your signal generator, the amplitude of the output signal is basically your volume control when you're testing a power amplifier. So the power amplifier has no volume control. It's not an integrated amplifier, at least not in this case, not what I'm testing here. So if you have an integrated amplifier where it has a volume control, then you can set the output to say maybe 300 millivolts or a half a volt or something like that. But when you don't have an integrated amplifier, so the input to this amplifier is, whatever signal goes in, it gets amplified to the full ability of the amplifier, and then, it's out to the speakers, or to, in this case, the dummy loads. So you want to start with a very low signal right here, so just 10 millivolts RMS. If I set this to say 300 millivolts RMS, it's going to drive this amplifier to probably near its full output. Be very, very cautious of that. Don't start with a high output. Always start with a very low output, because again, this is acting basically like your volume control. All right, so let's go down to the amplifier and do a full power output test. All right, let's try a full power output test on the amplifier that has the cosmetic issues. So I have the Fluke 199C scope meter connected to the left and right channels of the amplifier, and the scope meter is set to 20 volts per division on both channels. So initially you probably won't see much activity, but as the output of the amplifier rises up, then we should start to see some indication on the display. And the voltage values up here on the left and right channels for the A and B on the oscilloscope are given on those two numbers up there. So the amplifier is rated 150 watts per channel into 8 ohms, and that's 34.6 volts. So we want to see that we can achieve 34.6 volts, and watch for that indication on these numbers up here. Now I have 8 ohm dummy loads connected to the amplifier, and those resistors are rated at 300 watts, so they're well sized for this test. All right, so the function generator is set to 10 millivolts RMS. I'll start at that level, and I'll turn it on in just a moment. So let's turn the main power switch on here. Okay, there's a click, so that's the protection relay clicking in, so that's good. So this light that turns on the front is just sort of a graphic type symbol that lights up just to show that the power is on. But there's a bar graph display that's on each side, and that shows the power output on each channel, so I want to watch to make sure that's working as well. Also a range switch right here for a high and low range, sort of like a resolution that's on those displays. So I'll turn the speaker A switch on. Reach up here, turn the function generator on. All right, there we go. So we'll start to increase this. So it's at 10 millivolts RMS right now. There's 50. Okay, we're starting to get some indication. It's not triggering yet. It's just a little bit under the trigger level. A little bit more here, so we're up to, should start to trigger pretty soon. I can see the trigger indication on the display right there. There it goes. Okay, so 13.5 volts. Both channels are looking almost identical. So that's 400 millivolts RMS right now in the input. So again, we want 34.6 volts, or 23. There it is. So there's 35 on each channel. Perfect. 35.8, 35.4. So I'll turn the signal generator off again. And that's actually exactly at 1 volt RMS input. So perfect. That looks very good. So 1 volt going in, and it achieves the 150 watts of power. Basically just slightly over the 34.6 volts. So I'll turn that back on again. Yep, goes right up there, 35.8, 35.4. So no problems. The signal looks very good. I don't see any clipping or any distortion, nothing too serious. So it's looking very promising at this point. Now that I know that this circuit board is working correctly, I can tear down this amplifier, remove the circuit board, replace all the electrolytic capacitors, just do a general cleanup of the circuit board. It's quite dusty and dirty. Remove the old heatsink compound on the output transistors and just prepare that board to be installed in the other amplifier. And then in the other amplifier, completely tear it down, clean up all the internal components. Again, it's quite dusty and dirty. And once that amplifier is ready to start to reassemble, reinstall this board in the other amplifier. And then when the amp is completely reassembled, test it, make sure that the full power output is working correctly, set the bias voltages, make sure that there's no crossover distortion, that both channels have equal amplitude on the output signals, that there's no distortion, make sure the frequency response of the amplifier is working correctly. Just really go through and do a complete overhaul and servicing of the amp, and then test it and make sure that it is functioning correctly. So this concludes the part 1 video, and everything that I'm mentioning that needs to be done will be shown in a part 2 video, so stay tuned for that. So if you did enjoy this part 1 video, you can let me know by giving the video a thumbs up. And if you're enjoying the videos on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. Lots of projects in the queue. You won't want to miss any of those. So tap the bell symbol to be notified when I do post a new video. And again, the part 2 video will be coming up, so stick around for that as well, because there's plenty more still to do. All right, thanks for watching, and until next time, take care. Goodbye for now.